There's no sound in the recording. I realized that. I'm really sorry. I realized that like just now that my mic wasn't turned on. I'm sorry. I'm sorry. I'm going to start talking about this, and I want to talk about this from the perspective of this program. And what I'm going to do is, you've all got a copy of this in front of you, so I don't need to have a copy of this program up and running. But what I'm going to do is I'm going to pop up my tablet here, and I'm going to start kind of drawing some of this stuff out. So on line 35, this is the first one we're looking at. Line 35 is, we're calling fork. We're making the fork system call here. So one thing that our operating system might need to know about here is that a new child process has been created. So that's great. That's a good thing to notice. I'm going to be a little bit more specific about that. And I'm going to start drawing this out. I'm going to say struct PCB. I'm going to write this out as struct PCB. And I write this in black so that it's a little bit more visible. On line 25, our child process is created. So one thing that we get out of this is that we might need to know who our parent is. I'm not going to write pointers and stuff. That would be too much. I'm not going to write pointers and stuff. We might need to know who our parent is. So who created us? And this maps to that system called get ppid, get my parent's process ID. The other half of that is that I, as a process, might want to know who my children are. So who have I created? I'm going to put children PIDs here, and I'm going to write this as an array or a list or something. It's a collection. There might be a bunch of PIDs that we're getting as a result of this. On line 25, the OS receives and distributes signals. So on line 25, that's where we're registering our signal handler. So that line says signal, SIGUSER1, and handle. Our operating system here has signal handlers. So this process has some kind of collection of signal handlers. Our operating system needs to be able to know what it should ask or what it should tell that process to do based on a signal that is received by that process or is sent to that process. This is also going to be an array. This is kind of like this is a table. This is a table. I'm going to not use the word array to describe this, but instead I'm going to use the word table to describe this, but they're functionally the same thing. This is a table that's going to look like at entry 0, I've got a function pointer. At entry 1, I've got a function pointer. At entry 2, I've got a function pointer. At entry 3, I've got a function pointer. At entry 4, I've got a function pointer. At entry 5, I've got a function pointer. At entry 6, I've got a function pointer. And so on and so on. Yeah, okay, and so on and so on. We don't normally think of this just as 0, 1, 2, 3, 4, 5, 6, though. We're normally thinking of this as sig user 1, sig user, I cannot write, I'm going to write this more cleanly, sig user 2, sig term. Some of these function pointers are going to be that default. So politely terminate yourself. I'm going to call the exit system call when this happens. Ignore it. The function pointer might be a function that does nothing. Just there's no code in it, it just doesn't do anything. It might be that we have asked the operating system to replace whatever that default action is with what we want it to be. On line 25, the thing that we've asked our operating system to do is to take whatever's in the signal handler table at sig user 1 and replace it with this function handle. So when my process has that signal sent to it, I'm going to suspend whatever I was doing before, and I'm going to handle that with this function pointer. So our operating system has to keep track of this table so it knows what to do when a signal of that value is sent to us. That's great. There's no sound in the recording. Again, I'm sorry. I'm really, really sorry. Line 38, a signal sent from the process. So on line 38, we're running kill. We're sending a signal to another process. On line 28, the operating system needs to know about what signal handlers that process has registered for it. So that's another process that will have its own sig handlers table. When we run this, though, kill it's a system call. So this is that chapter 6 mode switch and context switch stuff. What our operating system is going to need to know about here is the state. And I'm going to write CPU state here. And I'll put registers. So when we call kill, we're basically saying, I would like to do a mode switch. I'm asking politely to go to the operating system and ask it to do something for me. This is our operating system and our hardware working together to save the state partially of what that CPU is right now for this process, and then the operating system finishes the job for that architecture. When we switch to this mode, to the operating system, we have to save that state before we can go back to that mode so that our operating system can use those registers to do what it needs to do. It's just a program. It's going to be using registers to do stuff in the same way that this process is using registers to do stuff. So we have to have that state in there. So the kill system call itself doesn't really need our operating system to do anything for us, but we do need to be able to keep track of the states, and this is going to be true for any of the system calls that we're making. On lines 18, 19, we're allocating resources and context switching. So lines 18 and 19. 18 and 19, we're creating this array of pipes, and we're creating this character pointer called megastring. Allocating resources. So malloc, I've kind of said this before, that malloc is not actually a system call, and it's not actually asking the operating system to do anything. It might indirectly ask the operating system to do something, but this is a function call that we're making to our standard library. The standard library, though, may ask the operating system to allocate more memory for this process. So I'm going to write here allocated memory. And I'm going to put in parenthesis physical. So when we started with processes and forking and stuff, we saw that, hey, these addresses in these two processes are the same, but we're making changes to them, and that's not actually having an effect in between the two processes that we've got. These are virtual addresses, but our operating system sits at a higher level than us, and it knows about what physical memory looks like. We're going to see this later, this idea of virtual memory, but our operating system has the responsibility of deciding which physical addresses go to the virtual addresses that we're looking at within the context of our process. Line 25, where our signal handler is being done. So I think we got that one. That's good. Line 21 needs to know what the file descriptor refers to. So line 21 here is int fh is equal to open myprogram.co read only. So our operating system here, in order to be able to give us a file descriptor, similar to this array of signal handlers, this table of signal handlers, we have to have a set of open files. So I'm going to write this open files. And this is called the open file table. When a process starts, it has by default 3 file handles. There's stuff in this open file table as soon as your process starts. You haven't called open, but there's 3 things in your open file table every time. At entry 0, so I'm going to write OFT. At entry 0, 1, and 2, there's std in, standard input. There's std out, standard output, and std error, standard error. Our operating system is keeping track of these things inside of this open file table. When we call open, it's adding an entry to this table. So we'll get 3. It might be like consecutively the next value, but it's meant to be opaque. So it's an integer, you know it's an integer, but you're not supposed to care or know why it's an integer or what its value is. You just have this thing. It's a reference that you can use. This is going to refer to, I'm going to write uppercase file pointer. But I want to be clear that this is not, it's not like the file pointer that you get back from fopen. It's not the same thing. This is talking about this in the operating system now and not in our standard library anymore. So when I call open, what I'm really asking the operating system to do is modify my process control block, modify my open file table, and add an entry in this open file table for me that points to this file that's somewhere on the disk. I want to go back to all answers, and I want to see, can you please move the box? That? I can't tell who's writing this. Is it a person in the room right now? Is this the box? Oh gosh, this is bad. This feels really bad today. Is this big enough? Is that okay? Or is it just like if I put it here, my video? I guess, yeah, it's my video being superimposed on it. Here, I'll put myself down over here. Okay. I'm actually kind of impressed that YouTube is keeping up. If this is somebody that's on YouTube that's asking this question, I'm kind of impressed that it's keeping up, because sometimes I go back to my office and it still says that I'm streaming. And I don't know what's going on with that. Okay, so it's keeping this open file table. And the open system call is asking this question, hey, can you add an entry to my open file table for me? This file pointer, I'm going to move over here. This file pointer has things like offset. So on line 28 in this file, we've got this while loop that's doing a read on here. The read system call is saying, can you please put some data from this file descriptor into my buffer? But also please move up in the file by that many bytes. So the next time I call read, I get the next set of bytes and not these bytes again over and over and over again. So our file pointer here has an offset in the file. And that part, this part, is being modified by read. So our open file table is modified by open. And our offset in file, our file pointer, is being modified by the read system call. On the address pointer, the stack pointer, the PID, the parent, and the child, the address pointer, stack pointer, PID of parent and child, address pointer, I'm going to interpret address pointer as the instruction pointer, the stack pointer. So these are all things that would probably go into the CPU state part. The one other thing that we haven't addressed here is on line 33. On line 33, we're calling that pipe system call. When we call pipe, we're also modifying the open file table. So this is modified by open and also pipe. Our open file table is modified by pipe. And what happens when we call pipe is that we have two entries that are added for us, two different file descriptors. The value that the file descriptors have here the value that the file descriptors have here is it's kind of like it's a queue. It's a queue. It's like a linked structure. It's a queue. It's a buffer, but it's a queue. I'm going to write just the letter Q because I don't know, maybe you're all guessing like me. How do we spell Q? How do we spell Q? There's U's and E's and a Q. We all know what Q is. This is a Q, and this Q, so I'm going to draw out this linked structure. We've got these two ends to this queue. There's the write end and there's the read end of the queue. The right end of the queue, I'm going to leave the letter Q here just to make sure we all know what it is. The right end of the queue points to that part of that one single queue. The read end of the queue points to the other end of that one single queue, that one single queue. So when I write to one end, I'm adding stuff into the queue, I'm enqueuing it, and then when I'm reading, I'm dequeuing from that same queue. It's not a linked structure in the kernel. It's not a linked structure, it's like arrays and stuff. But abstractly, it's a queue, a linked structure, and we can imagine it that way. When I write, I'm adding to one end of the queue. When I read, I'm pulling off of the other end of the queue. There's one thing that's not in here that I'm going to add right now in the moment, and that is a system call to close. The open file table is also modified by close, and also close. The close system call says, okay, I'm finished with it now. I'm done with that file. I'm done with it. I don't need to keep track of it anymore. I don't need this to be in my table anymore. So you can remove it from my table. What about its own PID? That is just up here. I don't have PID. Okay, thank you. PID. What's my process ID? We also need to know what my process ID is. Forget PID. So here's our structure. We have PID, parent PID, children PIDs. These are things that are going to be affected by the fork system call and the exit system call, I guess. Exit will cause this entire thing to be deleted by the operating system. When I call exit, I am finished. Operating system, please delete this process entry. I don't need to be kept track of anymore. Fork keeps track of parent PID and children PIDs. Signal and kill. Signal is making changes to this table of signal handlers. Kill is referring to the table of signal handlers, asking what is the action that I should take right now. Malloc might be referring to allocated memory, physical. Our operating system does have to keep track of this stuff. Our program here has some memory, like stack and stuff, that's part of its address space. When this program is loaded into memory, its code is loaded into memory. Our operating system has to keep track of the memory that we've got for this thing. The CPU state registers, we have to keep track of what this is doing right now so that when it is interrupted, or if it is in the process of being interrupted, I can put it back on the CPU without it really knowing that it ever left the CPU. We've got this idea of an open file table, and the open file table is an array of things that look like files, data streams, standard input, output, error, files, and queues. And these are modified by things like the open system call. Open is going to add new entries to this open file table. Pipe is going to add new entries to this open file table. And close is going to remove entries from this open file table. I'm going to step back here. And on line 35, when we call fork, fork is duplicating this entire thing. Fork is duplicating this entire thing. So here's what I'm going to do with this. When I call fork, fork duplicates it. Okay, copy paste. Good, copy paste. But while fork does copy paste a lot of this stuff, things are different, right? When we return from fork, PID is different. In the child's case, the PID is going to be something that's different from its parent. It doesn't have the same process ID. When we return from fork, we see 0. But that process still has its own ID. When we call get PID, it doesn't return 0. The parent PID changes to something else because it's got a different parent. The children PIDs is probably empty the first time it's created. It doesn't have any children. The signal handlers are going to be the same. They are duplicated, but within the code space of the new process that was created, because allocated physical memory is also duplicated. When I copy this process, I'm copying everything about this process. So anything that it is allocated in by malloc, for example, will be duplicated. The open file table is also duplicated. However, and this is where I'm going to stop, I think, this queue that we have here these are the same queue. So we fork, we're duplicating stuff, but the open file table, the queue that is being pointed at by my open file table is the same for both of those processes. This is what's allowing us to do like send data right to one end of the pipe in one process and read from the other end of the pipe in the other process. That queue that's sitting behind this is the same for both of those processes. Okay, so the last thing that I'm going to really quickly write down here is that the open file table can also be modified and also dupe 2, dupe 3. Dupe 2 says, I want to replace an entry in the open file table with something else. So I've got 2 file descriptors. One of them is going to be what I want to replace and what I want to replace it with. So, for example, you might want to replace standard input with the read end of a pipe. You might want to be able to read from a pipe, but it's standard input. You might want to be able to read from standard input, but it's actually a pipe underneath. Dupe 2 is allowing you to make changes to the open file table that way. Okay, so I'm gonna put this document. I know this is a crazy like mess of arrows and stuff, but I'll put this up on the course webpage for you so you have access to it. We may do this next class. I'd like to do this to see what the Linux kernel actually looks like, but we've run out of time at this point. You should, at this point, be able to write some code where processes communicate through message passing with signals, pipes, and FIFOs. FIFOs, we're just going to ignore for now. You should be able to compare and contrast these message programming models and their relationship as seen through the lens of synchronization. And you can now determine approximately what an operating system needs to know about a process. I hope that you all have a great weekend, and I will see you all next week. Goodbye, everybody.